Here we are again, and we're going to do part 2 of the KSP solubility video explanation. So yesterday you should have watched the KSP and solubility of substances that aren't very soluble in water. Today we're going to look at them in other solutions. And if there's a common ion in the solution, then that will affect the solubility. So let's get started with that. For this first problem, calculate the solubility of CaOH2 in 0.1 molar calcium nitrate, and then the KSP is given. So on our problems before, since it was in water, we were not worrying about the we said that the initial concentrations were 0. But now if this is in 0.1 molar calcium nitrate, then the original concentration of calcium will be 0.1. And the initial concentration of OH minus would actually be 1 times 10 to the minus 7th. But because the calcium concentration is so much higher, we're going to ignore that and just call it 0 for right now. So setting up our ice problem, then we have no concentration for the solid calcium hydroxide, and then 0.1 instead of 0 for the calcium, 0 for the hydroxide, plus S since there's just one calcium, plus 2S since there's two hydroxides. And so then at equilibrium, it'll be 0.1 plus S for the calcium and 2S for the hydroxide. When we set up the KSP expression, there's one calcium in calcium hydroxide and there's two OHs. So it'll be KSP equals the concentration of calcium times the OH minus concentration squared. When we look at that 0.1, we are going to, again, make the assumption that that plus S, that S is going to be a lot smaller than 0.1. So to make our calculations much easier, we're going to ignore the plus S from the 0.1, like we've done before in ice problems, and we'll just call it 0.1 instead of 0.1 plus S. And then we plug in 2S for the OH minus, and that has to be squared. So then plugging in for the KSP, 6.5 times 10 to the minus 6 equals 0.4 S squared. When we multiply that, solving for S, we end up with 0.0040 molar. We should always check that approximation to make sure it was okay to ignore it. And so 0.004 divided by 0.1, which was the concentration that we ignored it from, times 100 is a 4% solution. I mean, a 4%, it's 4% of it. So we said before, as long as it's less than 5%, then it's okay to make that approximation. So our solubility then is 0.004 molar. Okay, let's try another one. Calculate the molar solubility of silver sulfate in 0.22 molar silver nitrate. I looked up the KSP value. It's 1.5 times 10 to the minus 5th. So again, setting up our equation, Ag2SO4 for silver sulfate breaks into 2 Ag pluses plus SO4 minus 2. So now our initial concentration of silver is 0.2. It doesn't matter that there's a 2 there. That's the concentration that's given, is 0.22. So we don't double that. And then the change will be plus 2S plus S as it dissolves. And also, just a side note, since we already have silver in solution, this will be less soluble. It's going to shift the equilibrium that way when we already have some silver in there, common ion effect. Same thing for the previous one. When we calculated the solubility of calcium sulfate or calcium hydroxide in water, what did we get? We got a solubility of 1.18 times 10 to the minus 2nd, or 0.0118. Then in the problem I just did, when it was already some calcium in there that made it less soluble, so it's shifting the equilibrium this way, which means S would come out to be lower, and it did. It came out to be 0.004. So same thing on this one. We have this now in silver nitrate instead of in water. So the solubility is going to be less than it was in water. So same thing. There's two silvers, so it's plus 2S. There's one sulfate, so it's plus S. So it'll be 0.22 plus 2S. And again, I'm going to ignore that plus 2S, assuming that it's going to be small compared to the 0.22. Makes my math so much easier. Then I am going to solve for S. Again, there's two silvers, so it's the concentration of silver squared times the concentration of sulfate, which is S. So 0.22 squared times S equals the KSP, 1.5 times 10 to the minus fifth. So S comes out to be 3.1 times 10 to the minus fourth molar. Checking that approximation, I ignored 2S, so 2 times 3.1 times 10 to the minus fourth divided by the original concentration gives us a percentage of 0.28%, so that is fine. That's a small enough number that it was fine to ignore it. If I also try that in sodium sulfate, 0.22 molar, I'll have the same setup, but now I have some sulfate to begin with. So in 0.22 molar sodium sulfate, the concentration of sulfate is 0.22. So again, plugging in the plus 2S and S for my amount that it's going to gain. And I come up with 2S for the silver ion concentration and 0.22 plus S for the sulfate. Again, I'm going to ignore that plus S and just plug in 0.22. So 0.22 times 2S squared, since there's two silvers, equal to the KSP of 1.5 times 10 to the minus fifth. And my solubility comes out to be 0.0041. So having the sulfate as 0.22 did not change the solubility as much as having the silver, because there's twice as much silver. So when we look at these values, solubility is less in silver nitrate than it is in the sodium sulfate. Again, because there's only one sulfate ion, but there's two silver ions. So when silver's already present, it's making a bigger difference. It decreases solubility more than the sulfate did. Also checking that approximation, 0.0041 was what S came out to be, divided by the concentration that I was ignoring it from, comes out to be 1.9%. So that approximation was fine. Looking at hydroxides that are really insoluble, like iron hydroxide, iron 3 hydroxide, the KSP value is 4 times 10 to the negative 38th. So it's very, very insoluble. In cases like that, we actually do need to look at the hydroxide concentration because, again, it's so insoluble that S is going to be really small, so that hydroxide concentration is going to make a difference. So we're going to look at it in water, its solubility in water, where the pH is 7, and in a solution at pH 11, and see what the difference is. So again, because this KSP is so small, that's why we have to look at the starting concentration of OH minus when it's in water. So that's 1 times 10 to the minus 7th, since OH minus and H3O plus both equal 1 times 10 to the minus 7th when the pH is 7. So once again, same thing, we set up our ice it's plus S, it's plus 3S for the hydroxide. And so at equilibrium, it'll be S, and then this will be 1 times 10 to the minus 7 plus 3S. Putting that into the KSP expression, the 1 times 10 to the minus 7th plus 3S needs to be cubed. But again, I know that S is going to be very small. So I'm going to ignore that plus 3S and just use the 1 times 10 to the negative 7th value times the S. And that's going to be equal to the KSP of 4 times 10 to the negative 38th. When I solve for S, it is very small, 4 times 10 to the minus 17th. So I was definitely fine from ignoring it here, 10 to the negative 17th versus 10 to the negative 7th. Okay, now let's see what happens in a pH of 11. When pH is 11, that means pOH is 3, and then the OH minus concentration would be 1 times 10 to the minus 3rd. So now I'm going to do the exact same setup, but now I have a higher concentration of OH minus to begin with, and still plugging in plus S plus 3S, S, and then 1 times 10 to the minus 3rd plus 3S. I definitely can ignore the plus 3S here. Let's get my pen. And I can, it's not liking me to write right now, so I guess I won't. So the plus 3S we'll ignore. And when we plug it into the KSP, I see that my solubility now is 4 times 10 to the minus 29th. So that's even less soluble than to the negative 17th. Okay, so quite a bit less. And that additional OH minus was what made the FeOH3 even less soluble. Okay, so that's how you do it when you have some ion already present. It's not just water with some of them, or if it's a hydroxide and it's a very, very insoluble hydroxide. In that case, the OH minus in water does make a difference. The other thing I wanted to look at is just when we're looking at different salts, seeing whether or not the, what happened to the writing here? That's weird. Seeing whether or not the addition of acid or base affects the solubility of these insoluble salts. So with calcium phosphate, would it be more soluble in acid or base? Well, since phosphate is a base, then that means in acid, H plus is going to combine with a phosphate and make hydrogen phosphate. So it would be more soluble in acid since it is composed of part base. Whereas something like silver chloride, Ag is a metal ion that is small, but it's not very positively charged, so it's neutral. And Cl is the conjugate base of a strong acid, so it's neutral. So both of these would be unchanged in solubility in acid. Neither one of them reacts with acid. So AgCl is not going to be more soluble in acid than it is in water. Okay, how about okay, now my